Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refath Bari. Watch his videos to achieve your dreams.
Okay folks, welcome to the fourth lecture of linear algebra. Today we're again looking at vectors and linear equations. Here's the structure of the lesson. Number one, we're going to be multiplying a matrix times a vector. Lastly, our exit step will be identifying the entries of a matrix. So let's get started with the do now. What to do is multiply this matrix and this vector. So I'll give you a few seconds and I'll be back. Okay, so does anyone know how to solve this matrix vector multiplication? Yes.
Take the first entry of the vector and multiply it by the first entry of the matrix.
And any other ideas?
Yeah, so write 1
Okay.
and then 1, 2, 3
1, 2, 3,
and then write 2
2,
and then 0, 1, 3
0, 1, 3.
and the next one is
5.
5, 2, 3, 4.
Yeah, perfect. Okay, so now all we have to do is add these up. 1 times this vector would be the same vector. 5 times this, let's do it quickly. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. Okay, now let's do this vector. 2 times 0 is 0. 2 times 1 is 2. And 2 times 3 is 6. Now all we have to do is add these up.
1 out of 10.
So 1 plus 10 is 11. 2 plus 2 is 4. Plus 15 is 19. 3 plus 6 is 9. 9 plus 20 is 29. Okay?
Wow,
So-
that is a large vector.
Yeah. This matrix times this vector. So that's the answer. So let's move on to the lesson. Okay? Show you the relationship between solving a system of linear equations and solving a matrix. Okay? The key idea is that a system can be encoded into a matrix, and a matrix can be decoded into a system.
It's like derivative and antiderivative.
Just like that, yeah. It's like the function takes you to the matrix, the inverse process takes you to the system.
Yeah, why you don't do just all the way, just system of equation? I love and I respect.
Why are matrices needed for this process?
So that's a very good question. Why do we even need matrices? That's the question that linear algebra was designed to answer. We need matrices because number one, they're compact. What do I mean by that? Well, matrices, if you remember, they only have the numbers. They don't have the variables associated with them. So they're easier to work with in that way. But more importantly, matrices are designed to solve the fundamental question of linear algebra. It's actually a very good answer. It's how do you solve a system of linear equations? Now, my goal today is to show you this question, how do you solve a system of linear equations, is the exact same as this question. Okay, how do you solve ax equals b is the exact same as the question. So to tackle this idea, I want to begin with a specific example. Okay. Yes. And we will begin with a specific system of linear equations. So I have x, y, z equals 2, x, 2y, z is 3, 2x, 3y, 2z is 5. So the past 3 lectures, I've been showing you 3 pictures, right? The row picture, the column picture, and yesterday what did I introduce?
Inverse vector?
The matrix picture.
Yes.
Matrix.
Yeah, matrix picture. So today I want to look at those 3 pictures and find a way to connect them. Okay, so number 1 is what? The row picture. So row picture, we just look at the rows. The row picture, remember, is today we are working with 3 planes, 3 equations. You can work with any number of hyperplanes and any number of equations. But the row picture for this one is 3 planes meet at a point. I have 3 planes, they intersect at a common point, and that is the point I'm trying to find. So, what is my goal? Find x, y, z. Right? Pretty simple, pretty basic. We've seen this before. That's the row picture. Next is the column picture. Column picture. What is the column picture? Well, once again, it should be straightforward by now. We look at the columns, right? So we have, let's write out the equations. And as usual, I draw the columns in green. So, okay, what are the columns of this matrix? Maybe the live audience wants to tell me, yeah?
I wanted to ask something.
Oh, yeah.
Could you make a smaller system of equations from the 3-row consisting of only x, y, x, z, or any two combination of variables, and then work your way up from there after finding the two?
Yes.
Multiplying the row 1 and 2 by negative 1.
Wow, okay. So he's giving us a little bit foreshadowing. He's giving us the solution to this system of linear equations, and we will look at that solution very shortly. But before we look at the solution, I want to bring you back to the main idea. Okay, so from the do now yesterday, I hope you remember from the do now yesterday, we learned how to make the coefficient matrix from a system. So today I will do the same thing. I will make the coefficient matrix of the system. How do I do that? I just take the coefficients and drop them in. 1, 1, 2, 3, 1, 2. Okay, so that's the coefficient matrix. By convention, I call it A. A is capital because it's a matrix. Now, I'm going to multiply this matrix A by a column vector consisting of the variables I want to find. So I want to find what x, y, z is. Remember, I bring you back to the goal. Find x, y, z. Okay, so this is my column vector x, and it's gonna equal the vector I want. This is the vector I want. 2, 3, 5. By convention, I call this vector lowercase b. So I told you in the fundamental question of linear algebra that our goal was to solve this system of linear equations, and solving this system for x, y, z is the same as solving this matrix equation for x. Okay? We're not going to do the methods yet, but the key idea of this lecture is to understand that these two questions are the same. These two goals are the same. Same goal. Finding x, y, z for this system is the same as finding x for this matrix equation. Okay? So now we want to generalize this idea using a general system of linear equations. We looked at a specific example. Now we'll look at a general example. And by the way, our student was actually right. He said, take one of the first vector, take one of the second vector, take none of the third vector, and you'll get the vector you want. And you can actually check. If I just take this one out, 1 plus 1 is 2,
Wow.
1 plus 2 is 3,
Isaac, you saw
3
that?
is 5. Wow.
I know.
Very nice. Okay. So now we look at a specific example. Now I want to generalize this idea to all the systems of linear equations. So let's look at the row picture for this. In fact, row picture is very easy. It's these three equations. Now, what is this row equation really telling us? It's telling us that three planes are intersecting at a common point. And that common point is the solution we want to find. That's the row picture. Number 2, we look at the column picture. Column picture is very easy, right? A1, A2, A3. So I'm going through this fast because hopefully you've understood all the ideas we've gone through so far. And this is equal to the column vector I want. And lastly, the new picture the matrix picture. Okay, what was our matrix picture? Well, we just put all the coefficients in, right? We just drop all of them in. Okay, so now what I will show you in this general picture of how to solve a system of linear equations, we have our three pictures. We have row picture, we have column picture, and we have matrix picture. Now I want to show you the connection between the matrix picture and the system. This is my system, this is my matrix. My system has been encoded into this matrix. And if I want to, I can decode my matrix back to my system. That's the magic of matrices. All of this garbage is translated into this very short notation. And whenever I want, I can translate it back. So encode, decode, encode, decode.
Oh, so that's why you need matrices.
That's why you need matrices, yeah. Okay, now. So go ahead, I'll give you a few seconds. Also have any
So
ideas?
one. Okay, so it's gonna be 3 or 4. I don't know.
So we take the first
I already know. First,
First
1,
entry.
2, 3.
1, 1, 2,
Oh, 1, 1, 2, and then 1,
and then 1,
0, 3,
0, 3,
and then 2,
and then 2,
3, 1, 1.
3, 1, 1. Okay, so let's see. Let's do this. So 1 times any vector, that is the same vector. Okay, and let's see if our student here has any ideas. Okay, how can I multiply this scalar and this vector?
So, just 6, 2, 2.
Oh,
Multiply
perfect.
that. Oh, wait.
Yeah, perfect. Now how can I add these three vectors?
So, 1, 2, 6 is 9.
9,
1, 0, 2 is 3.
3,
And then 2, 3, 2 is just
7. Right? That's it. Thank you for watching.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.